All right, let's dive straight into this explainer on a manufacturing process that literally redefines how we join materials together. I mean, if you've ever assumed that welding absolutely requires a blinding arc, toxic shielding gas, and a glowing pool of molten metal, well, you are in for a serious surprise today. We're talking about friction stir welding. So here's the big question. Can you weld metal without actually melting it? It completely challenges everything we usually associate with welding, right? There are no sparks flying around, no molten pools of liquid, not even any filler metal. But despite missing all those classic hallmarks of welding, the answer is a massive, resounding yes. Here's a quick roadmap for what we'll cover today. 1. Welding without melting. 2. The friction stir tool. 3. Key process parameters. 4. Solid-state welding defects. 5. Friction versus fusion. And finally, 6. Building the future. Moving right into Section 1, Welding Without Melting, the Solid-State Paradigm. Okay, so friction stir welding, or FSW, is what engineers call a solid-state joining process. And that just means that instead of melting the base metal into a liquid puddle, intense friction heats the metal into this crazy, plasticized, almost dough-like state. The peak temperature actually stays firmly between 70 to 90% of the metal's melting point. And because the metal never actually liquefies, we completely sidestep all those awful issues like solidification cracking, porosity, and that softening of the heat-affected zone that make traditional fusion welding of high-strength aluminum such a massive headache. Let's look at Section 2, the friction stir tool, anatomy of a process. To actually pull off this plasticized state, we rely on some incredibly specific hardware. There are 4 sequential steps that map out exactly how a spinning, non-consumable tool basically mechanically stitches 2 pieces of metal together. Step 1, the tool plunges right into the seam between 2 rigidly clamped parts. Step 2, the friction starts generating all that heat. Step 3, the tool travels down the joint line. And finally, Step 4, it sweeps that hot, doughy metal from the front to the back, forging it together under immense pressure. Now, to do all that, the tool has a few essential components. First, you've got the shoulder, which rubs against the top surface. It generates most of the heat and acts kind of like a lid, keeping that squishy metal from escaping upward while simultaneously pushing downward. Then, sticking out below the shoulder is the pin or probe. Think of this as the actual stirrer. It dives deep into the seam, usually with threads or flutes to pull the material around. But here is the absolute catch. If that spinning pin goes too deep and hits the rigid steel backing anvil underneath, total disaster. The tool will either wear down instantly or just completely shatter. And the physics of this gets really interesting. Because the tool is spinning incredibly fast while also plowing forward down the weld seam, the forces on either side are totally different. On what's called the advancing side, the spin direction is exactly the same as the forward travel direction, so those speeds actually add up. But on the retreating side, the spin is fighting against the forward motion, so it subtracts from the overall speed. Because of this crazy dynamic, the inside of the weld nugget is inherently asymmetrical. It's exactly why procedures have to strictly specify which way the tool rotates. If you get it backward, the metal won't flow right, and you've literally just ruined a wildly expensive piece of aerospace aluminum. Let's hit Section 3, Key Process Parameters, Controlling the Stir. So, how do engineers actually control this hot metal dough without sniping the tool? Well, it all boils down to the heat input ratio. That's simply the rotational speed divided by the travel speed. This one equation basically dictates the whole game. Crank up the rotation and you get more friction. Slow down the travel speed and that heat hangs around longer. So a higher ratio means a hotter, more fully plasticized weld. A lower ratio gives you a cooler weld, which is actually great for preserving the metal's original strength, assuming you still get it hot enough to fully bond, of course. But it's not just about speed. To really seal the deal, the tool doesn't actually sit perfectly flat. It operates at a slight tilt, usually 1 to 3 degrees tipped backward, so the back edge of the shoulder can kind of iron over the metal and forge it down. Meanwhile, the machine is applying a massive downward plunge force to keep that shoulder in full contact. It's a tricky balancing act, really. You need enough force to forge the joint together, but if you plunge too deep, you'll literally crush and over-thin the metal. Moving on to Section 4. Solid-state welding defects, flaws without melting. You might be wondering, if nothing actually melts, how do things even go wrong? Well, solid-state welding has its own unique gallery of defects. First up is the kissing bond. This is where the surfaces are mashed together tightly, but they don't actually form a true metallurgical bond.
usually because the pin didn't go deep enough to break up the surface oxides. Then you have wormholes. These are literally internal tunnels left behind because the metal wasn't hot enough to fill the gaps. You can also get surface issues like a lack of fill or excessive flash. And finally, the exit hole. Since you're physically plunging a pin into the metal, when you pull it out at the end, it leaves behind a permanent keyhole crater. Troubleshooting these means tweaking machine parameters, not just adding more filler wire like a traditional welder would. And this leads to a massive, real-world headache. Because the metal didn't melt, flaws like kissing bonds don't have an air gap. They lack a volumetric gap. That means if you shoot an X-ray through this weld, conventional radiography will look right past it and tell you the weld is absolutely perfect. They are essentially invisible. Because of this, you literally have to physically bend the metal. Destructive bend testing is mandatory, just to prove the bond is actually real and won't fail in service. All right, Section 5, Friction versus Fusion, the ultimate showdown. When we put friction stir welding head-to-head with traditional arc welding, the trade-offs become super clear. On the plus side, there is zero melting, which completely eliminates solidification cracking. You also don't need to buy any consumables, no shielding gas, no filler wire, and the distortion is way, way lower. But there's always a catch, right? To withstand a plunging, spinning tool, FSW needs incredibly intense, rigid clamping and a heavy backing anvil. You definitely can't just drag an FSW machine out into a muddy ditch to weld a pipeline. The fixturing needs are a huge undertaking. Finally, Section 6, Building the Future, Limitless Applications. Because FSW fundamentally rewrote the rules of joining metals, it's unlocked some absolutely mind-blowing applications across industries. In aerospace, it's the go-to for those massive propellant tanks on rockets, using those tricky 2000 and 7000 series aluminums that normal welders absolutely despise. In marine manufacturing, it gives us perfectly flat hull panels, saving just endless hours of trying to hammer out warped metal. The auto industry is using it for massive electric vehicle battery boxes. But honestly, the coolest part, because it's mechanical stirring, FSW can weld things that were basically impossible before, like permanently stitching aluminum directly to copper, or even aluminum to steel. It's practically magic. And speaking of steel, that was always the holy grail. For a long time, FSW was stuck on softer metals like aluminum. If you tried to stir hard steel, the friction would just instantly destroy a standard tool. But not anymore. We now have hyper-advanced space-age tool materials, things like polycrystalline cubic boron nitride and tungsten rhenium alloys. These materials can actually survive the extreme heat and pressure, meaning friction stir welding is finally a commercial reality for high-temperature steel pipes and heavy ship decks. It all really comes back to this one beautiful, simple summary. The joint is formed entirely by the tool plasticizing and mechanically stirring the base material of both parts together. There's no magic filler wire, no protective gas bubbles, just an elegantly simple yet profoundly complex mechanical process that is totally rewritten modern manufacturing. Which leaves us with one final exciting thought. As these high-tech tool materials just keep getting better and tougher, what impossible metal combinations are we going to stir together next? That is the real frontier here, and it makes you wonder how much further this tech is going to stretch the limits of what we can build. I really hope this explainer shed some light on the amazing science behind friction stir welding for you today. Keep questioning how the world is put together, and as always, keep learning.